Hey physics students, it's Mr. Galileo coming at you again. This is the first video of several I'd like to put together about our current unit called projectile motion. So projectile motion is an example of a two-dimensional motion. So we have motion along two axes simultaneously. We could go along the x and the y axis. We form these sorts of parabolic shapes called trajectories. This was another research interest of Galileo. We're going to be using then our kinematic equations, or how fast, how far, combination, timeless equation. Look at things such as height of the parabola or the projectile, how much time it'll be in the air, how fast it's moving at different positions, how far then maybe the projectile travels forward. Just like really with the unit on free fall, we see kind of a clash of ideas, the old ideas of Aristotle and the newer ideas of the Renaissance and Galileo. So Aristotle had studied projectiles, and his explanation really of a projectile was that the object would be pushed along this trajectory. This force was transmitted through the air. It was called the impetus. It was believed then that the projectile would travel in this trajectory until the impetus was used up, and then it would fall straight down. Here's kind of a picture showing Aristotle's view of what a projectile did. Traveled forward or upward and forward under this impetus. When that impetus was used up, it would fall straight down. That view then was held for a long time, up to through the Middle Ages and really up to the beginning of the Renaissance. Here's kind of another picture of Aristotle's ideas here. See the projectile, it just falls straight down. With the development really of cannons, we see a kind of an increased interest to really understand these trajectories and the paths at cannonballs and other projectiles travel. And Galileo then kind of studied then this idea of projectile motion, and became, like I said, important to understand these trajectories. Galileo then and others realized that these projectiles really were not traveling in the sort of method that Aristotle proposed. Instead, then, these projectiles traveled in smooth, curved paths. But understanding the type of path was not easy. Now, we know Galileo, from what we studied in free fall and ramp motion, that Galileo used the inclined plane to really determine how objects moved down ramps. And he found that objects got faster and faster. We have uniform or constant acceleration for something like a ball going down the ramp. Well, he used the same sort of apparatus, the ramp, to kind of help him with projectiles too. And this is kind of what he did here. He basically put this ramp on a table, and he then allowed these balls to fly off the table, and these balls then were kind of inked, or it allowed him to find and to measure their locations when they hit then the floor, the surface. And by manipulating where the ball started, he was able then to come up with different positions, etc., and measuring this kind of curvature, this path that was obtained by the balls that went through the air. So where the balls then hit the floor, they left then these marks, and Galileo could measure then the horizontal and vertical distances and then the speeds that the balls moved. He was able then to determine then that the balls then traveled in parabolic sorts of arcs or curves. Here's some of the pictures here from what we see Galileo doing. You can see maybe the inclined plane here, and then some of the measurements that he would make depending on where the ball was initially placed on the inclined plane. So in this first video, what exactly do we want to do? Or what do we really want to talk about? I want to discuss the generalized nature of the projectile. We have two really types of motion that we see with the projectile. We have the forward motion, the horizontal, and then we have the vertical motion. We're going to find out that this forward motion is our constant velocity, CV. CV motion horizontally or forward. But once the object is in the air, then it's going to be in free fall vertically. So we're going to have then an accelerative motion vertically. So both of these sorts of ideas then or motions are kind of merged together in what we see as what we say is a trajectory. I like to break trajectories up into three types. So this type, for example, we saw off this table, I call then a type 1 trajectory. We start then with an object moving horizontally, and we see then kind of this half parabola. I call that then type 1 trajectory. I call type 2 trajectories then are full parabolas. So an object might start at the ground and be projected at some sort of an angle, and then it would end at the ground. We get a full parabola. So for example, maybe someone's kicking a soccer ball. It starts in the ground and then comes back down to the ground. Finally, then we have our type 3 trajectories, what I call type 3, and those are our asymmetric trajectories. So our starting, our ending heights are not the same. We get these kind of partial sorts of parabolas. Now, to show then these two types of motion, horizontal constant velocity and vertical freefall motion, I'll then complete a Logger Pro video analysis, and I'll do that within the video also. Again, I've created this video for my high school physics courses, and there's kind of a handout that I also have while I go through then the notes.
Okay, I'm here on page 1 here. So this is unit 5, and we're going to again spend a couple weeks with this. We're going to talk about one type of trajectory of type of projectile today. So a projectile really is any object. It could be a ball, it could be a cannonball, for example. Any object, we launch it with some force. You know, a force in physics is what's called a push or a pull. We'll talk about forces a little bit later, but we really don't care about how the projectile gets into the air. But it could be a foot, you know, if you're kicking a soccer ball. It could be a bat if you're playing baseball. That object then is projected in some way and then moves under the influence of gravity. And again, on Earth, we can see free fall, or at least approximate free fall, if we neglect air resistance. So what makes this a little bit complicated is that we've really got two types of motion occurring simultaneously. The object moves forward, but yet it also moves, so it's moving horizontally, and it's also moving vertically at the same time. And both types of motion are a little bit different. And we're going to find out that horizontally, that the object is moving at constant speed, or at least approximate constant speed, and then vertically the object's in free fall. Now, we're going to see that projectiles are very common in sports, and that projectiles create then parabolas of different type. Hey, I'm going to cut to some sports videos right now. You know, there's lots of different types of sports, right, that involve projecting a ball or an object of some way. And you can project a ball, you can even project yourself, like in gymnastics, right? A projectile is an example of what's called two-dimensional motion. We've got this horizontal motion that's occurring, and we've got this up and down motion that's occurring. And both of those occur simultaneously. So, for example, then each sort of motion is a dimension. So, projectiles is an example of what's called two-dimensional motion. Now, this unit can be kind of complicated. Why? Because of this dual motion occurring simultaneously. And you have to kind of keep our equation straight. Okay, you'll do fine, but just be kind of careful with the notes, with the practice problems, etc. Hey, let's go to the next page. Okay, think of maybe a baseball pitcher. So the pitcher then is pitching from the mound. And the pitcher is at some height above the ground, right? And the pitcher is pitching the ball fairly horizontally to begin with. And then the ball then moves forward and it drops down, right? And so we'd see a trajectory that might kind of look a little bit like this. This is what we call then a type 1 projectile. And what we get then is kind of half of a total parabola. So the ball then is moving forward, and what we can do is we can draw the ball here, the baseball, and what we can do then is assign vectors to the motion of the ball. And so horizontally the ball's moving fairly constantly. So we're going to draw these vectors the same length. Once the ball leaves the hand of the pitcher, then the ball will then be influenced by the full effects of gravity. But gravity can only then exert its influence downward, right? That's the way gravity works. It's a downward sort of pull. And so we see then that the object is gaining velocity vertically. So if we assign then labels to these vectors, we have Vx, that's the horizontal velocity, and we have Vy. Vy initially starts at rest, but it grows over time. You understand why that velocity in the y direction grows over time? Because gravity's acting on that ball or on that projectile. We get then half of a parabola. And this is what we call type 1. Now, we might see type 1 in baseball with the pitcher. We might see it in volleyball, maybe with, the volleyball player jumps up and blocks the ball. We might see this in tennis with the serve. Now, we also have several other types of trajectories here. We can have a total or symmetric parabola. So maybe what we see is somebody throwing the ball and maybe it's being caught by somebody else. And as long as the thrower and the catcher are approximately the same height, we're going to basically see a symmetric total parabola. And what we can do is then draw a line of symmetry, right? We can cut that parabola into two equal halves. We've got the left side and we got the right side. All right, the trajectory on the left represents the upward motion of the ball. The trajectory on the right then represents the downward motion of the ball. Now, next week I'm going to talk a little bit about type 2 parabolas. I just wanted to introduce the different types that we have today. Well, we also have then what's called a type 3 parabola. And a type 3 parabola, the starting and the ending heights are not equal. Now, with the type 2 parabolas, our beginning and ending height were the same. Okay, that's what leads us to then this symmetric parabola. But in this case, we get non-symmetry. So we get a parabola that might look something like this, or we might have something that might look something like this if we started below and we ended up then higher than where we started. So we get then a non-symmetrical parabola. Again, I'm going to kind of talk more about these types next week. Let's go on to the next page. A common type of a type 1 parabola that you might see is maybe a throw-in in soccer. Now, some throw-ins are more like type 3s, but if the ball leaves the hands, I don't know if you can see that arrow very well, but if the ball leaves the hands horizontally, then we're going to kind of see something that looks like this. It'll be a kind of a type 1 parabola. Now, I've made one of these and I'm going to do the analysis. So I'm going to stop the video and show you the analysis on Logger Pro.
Okay, well, let's do a type 1 projectile analysis. So let me go into Logger Pro, and I've created kind of a movie of a type 1 projectile. So let me insert the movie. And the movie's on my hard drive, so let's find where the movie is. Okay, this is just a short little video of me tossing the soccer ball in a horizontal motion. It might be considered like a throw-in. So let's just back the movie up to where it looks like it's coming off my hands horizontally. Okay, so that looks pretty good. It's going to be horizontal in motion. The soccer ball will maintain a trajectory like this. So let me do a right click on movie options, and let me click this, and then also let me click this to 2. That way we'll skip a frame every point. Let me scale out the video, and the ball I've measured to be about 20 centimeters. So I'm going to type in 0.2 meters here. Okay. And I'm just going to kind of isolate the center of the ball. And again, we're getting a couple of graphs behind us, behind the scenes. Okay, that looks pretty good right there. It looks like the ball had just hit the ground right there. Now look what we get. Fairly interesting sort of graph here. So let's isolate just the forward motion. Look what we have here. We have a position time graph, but we have a diagonal here. Do you remember, what does it mean really to have a diagonal on a position time graph? Yeah, you're right. It means that the ball is traveling at a constant speed. So this represents the forward motion of the ball. The ball, as it moves forward, is traveling at constant velocity. We can then get the slope, and let me kind of do this in a little bit larger font so you can see that better. So this slope represents that forward motion of the ball, around 6.43 meters per second. It maintains that constant speed forward. Well, what's going on though vertically? Let's click then again, this is a position time graph. Look at this. It's a parabola. It's a projectile, right? It's a parabolic motion, a quadratic. This is the same parabola though we saw with what type of motion? Do you remember? Yeah, you're right. It's the free fall type of parabola that we saw. Again, we can do then a quadratic curve fit. All right. And again, let me make that a little bit larger here. This A, we said, was 1/2 the acceleration. And for free fall, that should be minus 9.8 on our planet, right? If we double that number, we get approximately equal to minus 9.8. This is the downward motion that we have for this soccer ball, or for really any sort of projectile. Now, if we do then the velocity time graph vertically, the vertical motion is a diagonal on a VT graph. Again, the slope means something, right? The slope is at downward acceleration. And again, it should be really equal to negative 9.8. We're getting pretty close to that. So what's really going on with the projectile? Well, a projectile is moving forward. How is it moving forward? Constant speed. Though at the same time, though, it's moving downward. How's it moving? With what type of motion? Well, it's being pulled down by gravity. It's in free fall. That's what makes this type of motion a little bit more difficult for students. We have two things going on simultaneously. We have constant velocity motion going on horizontally and free fall motion going on vertically. It's accelerating vertically downward to the ground.
Okay, did you really catch then all that analysis? It looks pretty complicated, doesn't it? But we essentially have three basic types of graphs. We've got two position time graphs. We've got the horizontal, or the X time graph. That's a position time graph that represents the motion of the object or the ball horizontally, right? So what sort of generalized shape we get? Well, we get a diagonal line. And again, whenever we see a diagonal line on this type of graph, what does it exactly mean? Well, it means that the object is traveling at constant velocity. Okay, that's what's happening horizontal. Now, if the object is traveling fairly slowly horizontally, then we might see a fairly low slope. So the greater the slope, then, the greater the speed forward or horizontally for that object. And again, this slope, what does it really mean? It means the forward velocity or the speed of the object. That's one type of position time graph that we get. Well, we get then a second type of position time graph, and that represents the vertical motion. Right? The vertical motion. Well, the object for a type 1 parabola, it has to start at some height above the ground. And so we're going to get then that half parabola that I discussed with you on the previous page. So the object starts at some height above the ground, and then it comes towards the ground. But again, it doesn't do that instantaneously. It takes time. So the ball is moving forward and dropping down. And we can again use tangent lines. So the first tangent line is horizontal. That means the speed is 0, right? And then the tangent lines get larger and larger, but they get larger negatively, right? This is exactly the type of graph we saw with free fall, correct? So we would say then that that velocity grows vertically, right? I've got to put a little y there, Vy, right? Because this is showing us the vertical velocity, those tangent lines. So what really do we have here? Well, we've got parabolic motion, right? A quadratic. Free fall. So when we get the computer helping us here, we're going to get A, B, and C, right? That A is the important number. It represents 1/2 the acceleration. And for this, we should theoretically get an A value that's around -4.9, right? Because that's half of the gravity of our planet, right? Of -9.8. Well, we can also show this information really with a velocity time graph, right? And the velocity time graph then, so this is velocity in the y direction as a function of time. So the object starts vertically at a velocity in the y direction that's equal to 0. Okay, and then that velocity becomes more and more negative. But it becomes more and more negative predictably, linearly, right? So this slope here then is the acceleration. But in this case, it's the acceleration due to gravity, right? On our planet, we said then that that's -9.8, right? Meters per second per second. So this graph is really kind of like what we just saw on the previous page. Both of these graphs are showing us vertical motion, and it's telling us that the object's in free fall. It's being accelerated. What does it really mean? It's that this velocity is changing, right? It's growing, but it's growing negatively. That means the object's accelerating, right? So we got to be really careful again. This can be pretty challenging. Why? Because really both the horizontal and the vertical motions occurring simultaneously, right? So we've got horizontal motion, but that's constant velocity. Okay, so we can say, xf equals xi plus vxt, right? Well, that represents the velocity horizontal. It's constant, right? Now, vertically, then, we've got the how far equation, right? Since this is up and down motion, I'm going to call this then delta y equals VIYT plus 1/2 AT squared. Let me let you get that down. So I'm just applying, that's our how far equation, but I'm giving it vertical subscripts, right? Now, since the object's in free fall and it starts vertically from rest, since I'm just throwing the ball horizontally, this term goes away for type 1 parabolas. This A then is minus 9.8 because the object's in free fall. All right? Now, that's the how far equation vertically. We also have the how fast equation, right? So we can write Vy final equals Vy initial plus AT. But again, this VIY is 0. So this represents the final velocity in the y direction equals AT. But again, that A is negative 9.8, right? We also have the third kinematic equation, and we occasionally will use that also. But again, these are the common equations. Okay, so we really have pages 1 through 5 done now. And the next page represents some practice problems. And we're going to deal with that on a separate day of notes tomorrow. Hey, talk to you later, kids. Bye.